Yeah, thanks, Will. So my presentation is about dynamic quadrupeds for planetary exploration and some of the work that we have been done at ETH in the last 4 years. So before I start, a little bit of motivation. I think already in the session yesterday, we saw that the requirements for the mobility system are becoming increasingly demanding. Scientists want to go into really these painful places for engineers, like you're talking about craters, caves, islands, all of places which make it very difficult and require a system that is versatile enough to cope with these challenges. So, and I'm here to advertise that LEC systems might be a solution for this because they could allow us to reach to those areas that we had not been accessed before. And additionally, LEC system, because we are essentially working on robotic arms, also enables some more application. So we could think, for example, of using those limbs to manipulate or inspect the environment. And this is a functionality that might come for free and doesn't require an additional arm on the robot. So far we have seen wheeled systems in space, most famously the American rovers, of course. There have been already LEC robot prototypes in the past, and you can see some of those examples here on the left. And they have been around like already since quite some time now. But since the last decade or so, we see quite a rise in these new kids on the block here from Boston Dynamics and from other commercial players actually selling these systems and bringing them to a level of robustness where they're actually used in the real world. So, and then the question is a little bit about the interplay between all those machines. So now I want to focus especially on the LEC systems because there's a tendency that we can see. So the LEC systems for space that have been developed are mostly multi-LEC systems. They make use of static locomotion, which means they always have at least 3 legs on the ground at all times, which makes them statically stable. So you can imagine like a table. That makes it very safe. It doesn't require much computational power to move, and there's limited velocities you can achieve with this. So on the other hand, what we have seen now in the last years are these dynamically walking quadruped robots. And the difference here is that those don't need to have 3 legs on the ground at times. So they can have much less, like 2 legs or even 0 legs on the ground. But of course, as you can imagine, the balancing exercise is much harder to control in this case. But you can reach higher velocities, and you can also be more efficient at higher speeds. So talking about dynamic locomotion, you all know animals and vertebrates, they make use of these different types of gait patterns. So for example, we have here a trot in the top left, a dynamic lateral walk on the bottom left. And then we have some special gaits, which you see on the right-hand side. And the special thing here is that those are gaits that have a full flight phase during walk. So if you look in the middle, these are Hildebrand diagrams, and they describe the footfall pattern during one gait cycle. And the yellow part indicates when the feet are on ground. So in gaits without full flight phases, you will always have at least 2 feet on the ground. And without, there's even times in which there's 0 feet on the ground, essentially having a full flight phase. And why is this interesting? So if we look at human locomotion, we can derive a metric which is called the cost of transportation. It basically tells you how efficient or how much energy do you need in order to traverse at a certain speed. And you can get those characteristic curves. So this one shows, for example, that if we are walking at the speed of around 1 meter per second, we are very efficient by doing that. If you work slower, or if you try to walk faster, it's less energetically efficient. Eventually, if you want to go fast, we start to perform a running motion, which is a slightly different gait that we are performing. And there is, again, a certain minima at a certain level. So this one shows that we are also intuitively changing gaits depending on the environment that we are in. This has been also famously demonstrated by the astronauts on the moon, which started to perform this kind of hopping or skipping gait. And if you ever tried this on Earth, you would relatively fast would give up because you would see that this is very exhausting to actually do. Nevertheless, they are doing this on the moon. And this was spiking our interest because we are thinking of, okay, now we have this possibility to control quadrupedal gates. Let's try to change the simulation environment in the sense that we have also different gravitational levels and see what becomes more efficient and how does that influence this cost of transportation. So here in these diagrams, we can see on the bottom a trot and a dynamic lateral walk, so the gauge without the full flight phases. And then on top, we see the gauge with the full flight phases. And now if we start to decrease the gravitational level, we can see that the gauge with the full flight phases become increasingly efficient. The cost of transportation here doesn't have really a metric, but if you look also at the power level, you will see that the power level also drastically goes down. So we can conclude that gates with full flight phases becoming efficient at lower speeds, that they become increasingly efficient. And static gates are still useful, and you keep in mind that a robot that is capable of dynamic gates is also able to perform static locomotion. So that's why we developed SpaceBok. This was initially a student project, which was running for 1 year, creating this leg robot prototype for space. The robot is able to perform dynamic and static locomotion. It's an energy efficient system design, and basically was our platform to investigate how can we use dynamic leg robots in space. I don't want to go too much into detail, but one thing I want to highlight is the drivetrain, because this is something very different from wheeled locomotion, because we do really precise force control of the end effector, in this case, the foot. And for that, we need a really transparent actuation, which means we have a high torque motor combined with a planetary gearbox. And this setup allows us to control the joint torque purely by regulating the current that goes through the motor, which is proportional to the joint torque in the end. And another thing why we want to have this transparency is that we want to absorb shocks. So if you start to walk on ground, you can see these repeating impacts. And if you would, let's say, for example, put a harmonic drive there, that harmonic drive will break very quickly. But here, because it's a very transparent and very efficient transmission, you would just push these impact backs to the motor and they will not do any harm there. So, but coming back to this jumping locomotion, this is how it looks like with the robot on Earth. If you perform this kind of jumping motion, and as we decrease the gravitational acceleration, we can jump increasingly higher. So now there's two ways you can deal with this. So first is you try to reach these high jump heights, or you just lower the power your actuators can provide and do what you do on Earth in space. So, but we decided to go for the first option because we also wanted to have a robot which is capable of jumping on Earth. So we performed those experiments in which we basically try to do these repetitive jumps and estimate the energy consumption. We quickly realized that you can only do this if you take care of the attitude of the robot, because this motion is fairly different from locomotion when you're just walking in gravity. So instead of having most time on the ground, you spend most of the time in the air if you want. So you have to take care of the control. So we have this kind of mixed leg robot / satellite hybrid with a reaction wheel. We can show that we can very precisely estimate the jump height of the system. Here we have a total height that we achieved of 1.4 meters. And we also integrated springs in the legs of the robot to decrease the energy consumption that we have during these jumps. So, and this worked very nicely. We could reduce the energy that we require per jump around the factor of 2. And that's simply because the energy that we put into the jumping, we could recuperate mechanically by getting them back and forth through the spring. Now, this was 1D. We also performed experiments in 2D, during which we jumped on this very flat floor. This is at STEC in the Netherlands, where the floor allows us basically to have these floating platforms and simulate microgravity in the 2D settings. And of course, you can also play around a little bit with this. So here you can see the reaction wheel taking care of the pitch orientation of the robot and well, our control of the ground reaction forces taking care of the jumps that we are performing and the direction we want to jump. So this is all very nice, but in the end, I mean, what we really want to do is something like this. So nature is, in that sense, very inspiring because it shows us how we can do this much more agilely without having all these clumsy extra components. So we found that reinforcement learning actually is a very well and very good method to perform this type of locomotion. And during this, the approach is basically that you train a neural network in a simulation, and you basically teach the robot that you want to achieve a certain angle in the system, and then through thousands and thousands of tries, in which the robot is varying the position of the end effect and controlling the torques, it figures out eventually on how to do this motion. So and once you do this, you can also copy it to the simulation environment of the actual robot. And then the next step, obviously, is to deploy it on the machine itself. So this was our first test in which we had the trained policy, which we gained from the simulation, transferred it to the real system. And once you do that, you can do lots of very impressive things. So this is a full 3D landing with the robot, all in simulation. And you can see here how the robot just uses its limbs to control and tries to infer the ground and make sure that it lands on its feet. Once we do that same experiment that you saw earlier with the reaction wheel, we can also see that we reliably jump from wall to wall. And it's not so clear in this video, but the robot also really makes use of the wall. So it sees what is coming and then plays with the limbs in the way that it can control the jump in a stable way. And this is something which is very difficult to do with a model-based control. So here we just use the same neural network from simulation. There's no model really behind this. But of course, we still have the same problems that also exist with wheeled systems. So here we see the problems that we had on the American rovers, where the wheels were like going through this soil and sometimes even got stuck. And for 6 weeks, it took them to get them out again. And legs might be a solution to that, but it's not like legs, we have legs and then all the problems are solved. Because also legs have this problem that you create quite a high sinkage. You can imagine that with these small feet, if you walk on something very compressible, you sink quite deeply. And then it's also a challenge to walk. So we developed some passive adaptive planar feet for sand walking. So we had to increase the surface area to avoid these catastrophic sinkage that we might experience on very compressible soils. That requires in order to get basically a plane surface contact, you need to get an additional degree of freedom in the ankle, which we just left passive. So it has now some compliance there, but it also automatically brings the feet back into a zero position. Then we also did some studies on the grouser designs, because grousers really help a lot in order to increase the traction. And of course, you want to have it lightweight, because this is at the worst point of the system. So this is really the end effector. And if you make that heavy, that inertia will always contribute to your energy balance. So once you have this, we can also perform locomotion on slopes. So we were very lucky. This is the ExoMars testbed at Zurich, Switzerland. So right after the ExoMars rover was done testing, we were basically the next ones who could enter this facility and demonstrate that we can perform this locomotion on the slope. As we all know, in space research, like as soon as you can show it in like an environment which is somehow representative, then people get very interested. And this is from the very first test that we did on the very first day. So there was not much tuning, just one day to make it work on the slope, and already we could go up to the maximum inclination. And it's nice that Genia earlier mentioned this behavior of the soil, because I also believe it's incredibly difficult to predict those properties just visually. So this is the same soil. I think visually it's very hard to make a distinguishment here. So this is just loose, and this one is compacted. And you can see how vastly different the terrain properties are. So here we have a steep sinkage, maybe a catastrophic failure. Well, here it's more like concrete, like a really flat and hard surface. So we thought, okay, now that we have legs, why not use those legs to also probe the environment, like we would do before walking on ice or before jumping into a pool. You want to get some knowledge before you perform an action. So we developed this test bed, which is a single foot drop test bed. Here in yellow, we see the foot. And this whole mechanism, the only thing that it does is picking up the foot and letting it drop again. And then we have a soil container here that we can also incline up to 25 degrees in 2 directions. And in order to get lots of knowledge, we performed automatic testing. So here we can see how the foot is repeatedly impacting that soil. And because the soil basically acts as a damper, we can put some sensors into the feet and capture the vibrational response from that impact. And as Genia also mentioned, we need a lot of data in order to perform something useful with this. So we tried it on many different soil simulants and created a data set of 2,600 impacts, which we also open source for the people interested. Now that we have all this data, what can we do? So, well, first of all, we can also perform the same impact on the robot, which is important because you want to show that not only it works on that test bed, but also in the real world. And the nice thing is with 4 legs, you always have 1 leg free that you can use to perform inspection or manipulation tasks. So in this case, we use it to gain more knowledge about the environment. So with all that data that we got from those impacts and the signals that we captured from the sensors, we were able to, after some signal processing, to perform machine learning on that data. So we used supervised machine learning algorithm in order to classify the soil simulants that we had. So for that, we used the support vector machine. And we could see that on this data, which we still varied quite a bit, so in different angles and different directions, we were able to classify quite accurately the different soils. This also worked on the robot, slightly less accurate, but this is also because the data set that we had here was quite small. But the interesting part now is that we can also use this to generalize on other soils. So we took our trained model and then we fed it some impacts that we did on other soils. And if you imagine that image that I showed earlier, the 2 videos of the 2 different soils, it was nice to see that loose version of the soil was highly classified at the equally loose ES1 soil, while the compacted version was very close to a bedrock or ES3. So this somehow shows us that, first of all, we can classify soils with this, and we can also somehow predict the soil behavior. And if you can do that before you actually walk on the soil, you get much more safe in that environment. So, but ultimately, this is all relatively low TRL level research. What we want to do, of course, is to go to space some point. And just as an inspirational few last slides, what we found is very interesting is the Alestahos Plateau, because it has all those interesting things. So we have here a very diverse, geologically very diverse terrain that the scientists love. So we have volcanic terraces, we have exposed bedrocks, we have this central uplift, potentially mantle material from the moon. I think this is a very, very interesting scientific site, yet very difficult and complicated terrain. So I think a leg robot or a wheeled leg robot would be a perfect candidate to explore such an environment. So we did some investigative studies and see how could our robot scale for this scenario. We gave it some instruments like a spectrometer, a microscopic imager, and a couple of cameras. And then we tried to shrink the system as much as possible. Of course, you can see it's not the robot that we have because we need to have some means to generate power on board, and we have to take care of thermal management. But this is just a vision, like an idea of how such a system could potentially look like. And then once you have that, you can already plan, some traverses. These are just some examples of route. And my dream really one day is to see a robot starting at the crater rim and then somehow descending into those interesting environments. So to conclude, I think dynamically walking leg robots have quite a potential for space exploration, especially in these areas where we have not been so far. Then dynamic gates especially are useful to exploit low gravity scenario. And reinforcement learning, I think, has a great future. I think one question later for the panel would be to see how we can test those systems or how do we convince people to trust them. if you can show them that they work on Earth. And then the feed we developed really helped to decrease the sinkage, to basically make the robot much safer in the terrain. And then lastly, well, tactile inspection or using the limbs is also something very useful and should be taken into account when thinking about which system to send next. So yeah, with this, I would like to conclude my talk. And yeah, if you have any questions, feel free.
Thanks, Hendrik. We're running short on time, but Olivier's got a question in the chat. Could you comment on the benefits or disadvantages of using limbs with more or less degrees of freedom? Robots like RoboSimian seem to have more degrees of freedom, but appear to perform slower than SpaceBok.
Okay, yeah, maybe briefly, I think, yeah, RoboSimian has more degrees of freedom, it's true. That makes it also more complex, but it also has the wheels. So potentially the cost of transportation, which I mentioned, might be much better if you're in a flat environment, because you can just roll that very efficiently, while if I have less degrees of freedom, then I somehow have to walk it, which might be more energetically efficient. So it's very hard to make the trade-off. I think it really highly depends on the mission scenario that you want to send the robot to.